Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so is this working? Yes. We are thrilled to have David Gamarnik from all the way next door, and he's going to be talking about statistical physics, interpolation method, and scaling limits in sparse random graphs.
Thank you. Thanks, Jennifer, and I guess Christian, even though it's not. Right. It's okay. I mean, I've been to many talks, and I know it's not. I don't take it as a personal reflection. He's always late, so it's. So I realize it's not me, and but nevertheless, thank you very much for the invitation and opportunity to present this work, which is a joint work with Mohsen Bayati from Stanford and Prasad Tetali from Georgia Tech. Hey. Well, let me say it again. So I wanted to thank Jennifer and Christian for the opportunity to present this work. And also, let me just explain this depressingly dark colors that I'm wearing, which was not my intention, but apparently your instructor to wear dark clothes as your speaker because
and
you're
no
well, I missed that. So because I deeply care how I look on the video recording, I decided to comply and actually do that. So I hope the title didn't scare you because I put a few buzzwords there, but in fact the only thing that I want you to know for this talk is what the graph is. Everything else I will define and explain. So hopefully you will, everybody will stay tuned. So let me begin with a few things that I'm not going to talk about in a detail, but just to set things sort of set the stage. Now it's been already maybe about 30 years or so where it was realized that a certain algorithmic questions in combinatorics and in general in statistics also, but primarily in combinatorics, are easy or difficult depending on depending on certain properties which apparently have some connection with statistical physics, and specifically connections with the phase transition properties. So loosely speaking, you're likely to be able to design a fast algorithm, some polynomial time algorithm, if the system does not exhibit a phase transition, and you're likely not to be able to do so if it does exhibit a phase transition. And this was largely more of a sort of a belief than actually hard statement until recently. And the recent culmination of this insight is actually the following theorem, one part of it which was proven by Dror-Weitz and the other part by Alan Sly. If you put together, you get the following extremely interesting fact. I think it's quite interesting. So the setup is you have a finite graph, and you want to count the number of independent sets in this graph. Just to remind you, the independent set is a collection of nodes such that there's no edge between the nodes. Okay? So you have a graph, you have a whole bunch of independent sets there, you want to know how many there are. It's a classical algorithmic counting problem. It's sharply hard, so you have to resort to some kind of approximation results or attempt to do some kind of design some approximation algorithms. Turns out that you can do that in certain weighting settings. So instead of counting independent sets, suppose for each independent set you put e to the beta times the cardinality of the independent set. So this is a generalization, because if beta is equal to 0, this is just a number of independent sets, but if beta is not 0, it's something more general than that. Okay, so you want to compute this quantity in a graph, and it turns out you can do that approximately in polynomial time, deterministic polynomial time, if and only if this parameter beta is at most a certain threshold. If it's less than this threshold, you can do that. If it's bigger, you cannot do that. And this threshold is actually not just some random number. It is actually the onset of the phase transition and associated infinite graph model, whatever that means. Okay? I don't want to go deep into details of what is the meaning of this phase transition point, at a high level, it's certain property associated with statistical physics. That's not a combinatorial thing that you would look at otherwise. Okay? And it's tight. So this is a really marvelous result because it tells you that the onset of hardness is the onset of is a phase transition. Okay? And to contrast it, maybe I should be standing here, and contrast it. Well, in the setting of independent sets, approximation, etc., in a very narrow setting, there is the connection. This only applies to independent sets. This only applies, but at least this is the first hard connection between the phase transition and complexity. It presumably would extend to other models, but at this point, this is what we know. On the other hand, if you look at the closely related problem of counting partial matchings, and just to remind you, a matching is a set of edges such that no two edges have a common node. It's again a classical Sharpie-Hart counting problem. If you want to count the matchings, you can actually do that, or do the weighted count of matchings. You can do that for all beta. And the explanation is that the reason you can do that is because matchings don't exhibit phase transition. There's no phase transition. You can count it always. Okay. So what do we have here? So we have a phase transition and connection with algorithms. These results are new, but the phase transition is old news as far as statistical physics is concerned. It goes back to 40s, work of Onsager and etc. So as far as the physics is concerned, the insight is kind of old, but the results are new. This is not what I want to talk about, though. I want to talk about something more recent. Some developments, more recent developments in statistical physics, which also appear to have interesting insights and relevance to random structures and algorithms. So far, we have managed to use it more for some establishing certain structural properties rather than algorithms, but hopefully this will go beyond. Let me give you a brief sort of timeline of what I'm talking about. Starting with 60s, and by the way, stop me if anything is not clear, or if you want to make any comments or anything. So starting from 60s, the theory of random graphs began. Now, when you say today a random graph or Erdős-Rényi graph, usually people would think about social networks or something like that. But actually, back then, it was not the social networks was not in minds of people who developed this. It was mostly combinatorics. So trying to prove some results about extremal properties of graphs, Erdős and Rényi developed this interesting random graph model that I will talk about later. Okay. Later on, about 80s and 90s, an interest was developed in trying to perhaps connect the randomness and graphs with algorithmic questions. So the idea being that, okay, so you have your favorite NP-hard problem, maybe you develop some kind of a heuristic. How do you check that if this heuristic works well? One natural thing is to maybe generate a random instance of your problem and see if it works well. And that led to an interest in the so-called random satisfiability problem. And immediately, a whole bunch of problems have appeared. It turns out that it's not only it's hard to develop good algorithms for these random instances, it's actually hard to even say something even structurally about these problems. For example, what is the likelihood that the random instance of k-set problem is satisfiable or not? So beyond algorithms, it's already becomes.
By the way, the physicists were already in the late 1980s. Those physicists who always get the physics wrong. What's his name?
Parisi?
No,
No, he got it right, I think.
there was this set paper by Bart and who was the physicist?
It'll come.
It'll
Okay,
come out
okay.
to me.
But in that's true. But in 90s and early 2000s, the physicists have particularly.
Patrick.
Oh, that's for Sherrington-Kirkpatrick model. That's probably what you.
It's a random case set.
Yeah, that's late That's like the 80s. It's more like 80s, 89. Yeah, so, okay, so, right. But close enough. Okay, so it's an FPTAS for the numbers here. And they have basically entered the picture and barraged people with a whole bunch of buzzwords. So replica symmetry, breaking, cavity, condensation, whatnot. And it was hard to make sense all of it, but you could sort of safely sort of disregard all of that if you wish, because you could say, okay, all of this is non-rigorous. This is just smart insights. Seems to be consistent with experiments, but none of this is rigorous. So go ahead and you actually go ahead and prove it something, and proof they did when they later on they introduced the so-called interpolation method. That's what I want to talk about today, which actually is a mathematically rigorous approach, and it allows you to actually prove some things about random structures. And and I'll talk about in detail so what they managed to do with this method. But the way it was introduced and explained, it was wrapped up in lots of statistical physics jargon and terminology, which made it extremely hard to parse, to understand what's really going on. And the goal of this work is to introduce this method purely from combinatorial perspective and convince you that it's actually a very, very simple idea. Very simple idea. So that's what I want to talk about today. The idea is to give a simple, tractable combinatorial treatment of the interpolation method and see what it gives us. Okay? All right, so that's the end of high level. Let me set the stage now. I want to talk about only one random graph model, and that's a standard vanilla random graph model called Erdős-Rényi graph. It's very simple. We have n nodes, and we create c times n many edges chosen uniformly at random, which means that c times n times we choose two nodes connected by an edge. And we repeat it c times n times, c n times. So in other words, this EC is just some scaling constant here. What we do is the number of edges is linear in the number of nodes. That's all it means. That's all I want. Okay? So, all right, so this is a graph. Physicists call it diluted spin glass model.
Not really. But
Yeah, at least in some papers they call it. We can argue later about that, but I can demonstrate at least one paper. It's by statistical physicists, and it's called diluted spin glass model. But okay. So on this model, let's introduce some combinatorial optimization problems, essentially. Now, I'll have a sort of maybe not very familiar language to introduce those in some unifying way, but you will shortly see that I'm talking about something that all of you know well. So think about assigning colors to nodes, and the choice of colors is around from 0 to some positive integer q. And suppose that for every node in the choice of a color, there's some value associated with that. It's like a reward that you get if you do that. And also for every pair of nodes, in fact, for every edge, and for every assignments of colors at the ends of the edge, you have some reward associated with that. If you are from the EE community, you would recognize this as a Markov random field model. Okay? These are node potentials. These are edge potentials. That's what it is. Okay? If you're in physicists, you would talk about Gibbs distribution, etc. If you're in combinatorial optimization, this might not be very familiar, but shortly you will see that many examples are exactly what we talk about in combinatorial optimization. Okay. So for every such an assignment sigma of colorings, then you have some associated quantity where you just sum up the node potentials and the edge potentials. Then you consider the so-called Gibbs distribution, where for every coloring assignment, there is associated probability, which is e to the beta times this total potential and some normalization constant, which is called the partition function. Okay. Let me give you a couple of examples.
Beta can be both positive and negative?
It can be both positive and negative, yeah. Although in fact, this definition is almost irrelevant for me because I will talk about optimization, and in optimization you look into something different. So, but yes, beta could be positive or negative. For example, an Ising model could be. It's interesting in both regimes.
It's the Russian probability notation that says e to the plus beta.
Is
The
that?
American physicists do e to the minus beta.
And then you
Russian
have
physicists
right,
do e to
and
the
then
plus
but then
beta.
you would have to put another
Right,
minus here.
exactly.
So physicists do this kind of a double minus game, which actually to me minus minus is plus, but maybe but maybe this is disagreeable. I don't know. So okay, so let me give you my first example. That's the main example that I want to walk through the talk, and it's what I mentioned already before, the independent set. So here's how you can frame an independent set in this terminology. Think about the following node potential function. Every time color 1 gives you value 1. Color 0 gives you value 0. Okay? And also for every edge, 1, 1 gives you minus infinity. Everything else gives you 0. So it's essentially what it does is does the following. Every time you have a sigma, sigma is an indicative function of some subset. If this subset is an independent set, then h of sigma is just the cardinality of this independent set. If the subset is not an independent set, then h of sigma is minus infinity. Right? I haven't done anything sophisticated. I just wrapped the independent set problem in terms of the Markov random field. Okay? Here's another example, partial Q colorings. Assume that all node potentials are 0, and edge potentials look like this. Every time you have a different color, you have a reward 1. Every time you have a same color, you have a reward, no reward, 0. In that case, h of sigma would be basically the number of edges properly colored by this coloring assignment. So it's like a partial coloring. Okay? So, okay? And then you can do it for other types of models. There is a Ising model, which is one of the most favorite models in statistical physics. You can also talk about max-cut problem here. You can encode by sigma whether nodes are on the left and the right, and then count how many edges go across the cut. So max-cut would be an example of this. K-set would be sort of an example of this, except I need to introduce hyper-edges instead of edges. Good. Now on this, rather than looking at the Gibbs distribution, I want to look at the following thing. Given a graph and given this 8 node and edge potentials, let me look at basically the optimized object. I'm looking for the sigma which maximizes the total potential. In the combinatorial optimization setting, all I'm talking about is largest independent set or largest partial coloring, max cut, whatnot. Okay, all framed in this unified way. Okay. Well, here's an annoying thing. For many of these problems defined on random graphs, it is rather straightforward to show that the optimal object scales linearly with n. So, for example, think about the independent set problem. So we have a Erdős-Rényi graph. We have an independent set. We're looking at the largest in cardinality independent set. It is a simple exercise, which you still need to write a few lines, but to show that there is linearly many in n isolated nodes. Okay? Now, isolated nodes is an independent set. So the largest independent set is at least as large as this lower bound. So you know that this quantity scales linearly with n. Okay? So you know that. On the other hand, this quantity cannot be larger than n for independent set, for example. So you have a lower bound which is linear in n and upper bound in n. Okay? And it's very natural to predict that as you take the expected value of this, maybe that's something, well, it scales linearly with n, maybe that's something you can compute. What's the size of the largest independent set in the random graph? That's a reasonable quantity to look at, algorithmically or not. Well, the annoying thing is that not only we don't know how to compute this quantity, we don't even know whether this actually limit exists. And I mean, it would be completely unreasonable to expect that it would not. Why would it not exist? I mean, you have a large things, and for those rare examples where you can compute it, indeed it exists, and you can compute. For matching, this is a notable exception. You can actually compute this limit for matchings using something called Karp and Zipser algorithm. You can do that. Limit exists. You can compute it. In general, however, not only, as I said, not only we don't know how to compute it, we don't know whether the limit exists. And this is this was stated as an open problem in a few publications, and among those, let me highlight Aldous's early installation of his favorite 6 open problems in 2000. This was problem number 2. And that also caught my attention as well, because it's just it should be painfully obvious that this limit should exist, but there's no technique to handle that. That's the
problem is for some age, for all age.
You would imagine that this should exist for all edges. Well, if age corresponds to, for example, matchings, then in that case we know. So in some cases we can.
We take the expectation with respect to the randomness of the graph.
Yes.
And what's the Gibbs measure?
No, there's no. This is optimization. This is just an optimization. Let's say. Have a random graph. I have some combinatorial optimization.
Minimum of the
H was the maximum. H was the maximum.
Right.
So H is the
Minimum
maximum.
for him because he has a minus sign.
Yes,
But yeah,
yes.
we know.
I would prefer to think about this as a bunch of examples. Think about largest independent set. Think about the largest max cut. Well, think about max cut. Take a max cut on the average Rayleigh graph, normalized by n. Again, it's easy to show that it's actually linear in n. Show that the limit exists. Conjecture is the limit exists. So does that answer your question? Yeah.
Like, it's not known for max cut, or not known?
It's not known for max cut. Not prior to this work.
So, by the way, is these things easier or harder for the related model of the random C regular graph?
For a random regular graph with bounded degrees, a similar conjecture applies. And again, it's not known. Again, prior to this work, it's not known. With a notable exception of K-set, and this is where statistical physics come in. I'll talk about that. Okay. Other questions or comments? Okay. So, well, as it turns out, that for one particular model, namely the Boolean satisfiability model, which I have not defined, but many of you know what the satisfiability problem is, when you look at this problem in the random setting, you can actually show that this limit exists, and this is what Franz and Leone did using the interpolation method. To be more specific, what they did is establish the following. You look at the random instance of a K-set, consider the maximum number of clauses that you can possibly satisfy, divided by n, the limit exists. So that's what they did. Okay? And they did it using the interpolation method, but the first time the interpolation method was introduced by Guerra and Toninelli in a different setting, in the setting of so-called Sherrington-Kirkpatrick model, which is well-known model in statistical physics, but not so much in combinatorial optimization, so let me not talk about it much. There is a follow-up work, Panchenko and Talagran, which gives us some kind of a unified treatment of Franz and Leone, and also uses the interpolation method. And so, to me, the interpolation method, I guess, started with this Guerra and Toninelli, but if you attended Martin's class yesterday, you've heard about the interpolation method to show an upper bound on which you can use for some concentration results. So maybe that's the origins of that actually goes even earlier than what I thought, and maybe I don't know if you. So it's
the same, or
well, it's a very similar procedure in where some convexity property is used. You interpolate continuously between two extremes, and you show that you have a definite sign in each derivative point. So it's very similar in spirit, but the setting is different, as I remember from your lecture. Okay, and the upshot of this interpolation method is it enables you to show that this numerator here is actually a superadditive sequence, and superadditive sequences are known to be converging after normalization. So that's the basically the framework. Okay. Yes?
So if you look at satisfiability, then for some C the answer is 1, for some C the answer is 7 over 8, and we knew it before, so the point was to get it like near the threshold to show that there is a limit?
I'll talk about that shortly. I have a slide just for KSAT. So how about I postpone this later on?
For KSAT it was only known for even K, right?
Well, they pretty quickly figured out that for odd K that actually works, and this was some communication that Andrea Montanari and Elitsa Maneva realized and told them, and they said, yeah, it turns out you can do it for odd K. But they also use some kind of a symmetry of KSAT problem that, at least in our approach, we don't need this symmetry. And as you will see, the approach is actually quite straightforward. Okay, so the way they did it actually is a bit slightly convoluted, not so unnatural for a physicist, but but for maybe in optimization, that's not the most natural way to look at it. They look at the Gibbs distribution, they look at the log partition function normalized by n and show that this limit actually exists, and then they just take beta to infinity, and from the partition function show the result for the optimization. And I'll convince you that you don't need to go into this kind of a roundabout way. You can do it directly. Okay. All right. So now let me state the results. So the first and perhaps the most relevant and interesting result is indeed this limit exists for a certain class of models, which includes the independent set, partial coloring. I said coloring here, but I meant partial coloring, Max-Cut, and K-set. Though K-set was already done by Franz and Leone. So that's the first claim. Indeed, the limit exists, and indeed answers positively the conjecture by Aldous, and the other and same conjecture stated in several other papers. So, for example, if you take the again Max-Cut in the Erdős-Renyi graph normalized by n, this limit exists. Unfortunately, we can't say anything about the value of this limit. All we can say is the existence. Yes?
Is this saying that you know it exists for all Hamiltonians in your notation H? Or just for the Hamiltonians?
Just for Hamiltonians associated with this.
Can you give an abstract statement of the set of Hamiltonians to which your result applies?
Yes, this is more of a recent work, and it's. I was only able to do that in the framework of partition function. But it turns out that if the Hamiltonians are such that the associated matrix is positive semi-definite, then, or you need to do something with it. But if you do something with it and it's positive semi-definite, then you have this limit, and that covers previous models. But a priori, it was not actually obvious what's the unifying model. But it does not apply to all H's.
So which matrix? E to the beta is the pair potential, or
yeah,
the
turns
pair
out
potential itself?
what you need to do is to take the maximum of e to the betas, and from that subtract all the other elements. So you need to take not the matrix, but maximum element minus matrix. I can talk about that maybe later. But there's some rather not too complicated functional property of the matrix of potentials. Okay?
So in my word, if the ground set energy is 0, then it's just positive definiteness of e to the pair potential.
I'll need to parse that. I can't do that one.
Well, you subtract the maximal element, right?
But it's not in terms of ground 0. It's in terms of the parameters of the model. I don't know what the ground 0 is. Let me talk about the satisfiability conjecture, because a few of this might actually miss some of the audience. So those of you who are not familiar with the development of random satisfiability I apologize. You might not fully sort of understand what's the setup. But one of the things that was at least attracted a lot of attention is the so-called satisfiability conjecture. And the conjecture is that for random K-set model, there is should be some critical C star such that if you're below this C star, this parameter C, this parameter C, to remind you, is the ratio of number of clauses to the number of variables. If it's less than C star, then with high probability this instance is satisfiable, and if it's bigger than C star, with high probability is not. That's a conjecture. And this is still an open problem. This is not resolved. But using this approach, you can sort of prove it in the following sense. If there exists some C star, such that if C is less than C star, then you can satisfy almost all of them. So the number of number of clauses, little o of n. Number of clauses that you are forced to violate is going to be little o of n. If you're above, then the number of clauses has to be linear in n. When C grows further, then it approaches the 7/8 that you mentioned. So what it basically means is that for every C there is this limit. At some point, up until a certain point, this limit is all the clauses, and then it starts dropping gradually. But the existence of this limiting behavior follows from the interpolation method by Franz and Leone.
Conjecture to be equal to the satisfiability threshold?
I'm sorry?
Is C star conjecture to be equal to the satisfiability threshold?
It's just, yeah, that's the belief that this is precisely, in other words, it's unlikely that there is a whole range of C's such that you can satisfy almost all of them, but not all of them. That would be unlikely. I haven't seen this explicitly stated in any of the papers, but that's the belief. Are there questions or yes, Martin?
So your original theorem is about an expectation, whereas this is with high probabilities or some
Yeah.
concentration
Okay. So
statement?
actually, it's actually from expectation you almost immediately get high probability statement, because the concentration of this quantity around expectation follows just from Azuma.
Okay.
For optimization, it's a Lipschitz function.
But your graphs have unbounded degrees? Do they
Graphs have
logarithmically growing degrees, or
no, average degree is bounded. Average degree is bounded
maximum grows?
maximum is like a log or something.
Okay, but average is enough.
Average is yes, and it's these objects have a Lipschitz continuity property. So if I change one edge, that can change my independent set by at most one. So it's fine. So the concentration is not a big deal. It's actually getting the handle on expectation itself. That was the open problem. But from this now it follows that you have a high probability convergence as well.
Do your techniques give ways of generating approximations to C star, or just the existence of C star?
Just existence. I mean, you can do some kind of a brute force numerics maybe to get the lower bounds on that, but nothing clever. Well, but there's other approximation. There's other techniques based on the replica symmetry method that give you, thanks to the interpolation technique, you can show that they give you up bounds on C star. But that's not my work. That's what Franz and Leone and Talleyrand and Panchenkov did. Okay. So that's what I wanted to say about connection with the satisfiability conjecture. What else? The remaining couple of results are perhaps less interesting, but let me state them in any event. The physicists, just to remind you, they started with the log partition function and proved that log partition function after normalization has a limit, and we can do the same for this scope of models that I've defined. And also you can show some kind of a large deviations property for the satisfiability itself. So what it means is that, for example, take a k-set model in the regime where it's with high probability non-satisfiable. There are some regimes you can prove that with high probability it's non-satisfiable. The likelihood of satisfiability goes to 0 exponentially fast, and you can have an upper bound on the rate on the exponent. But using this approach, you can show that this exponent is well defined. So if you look at the log of the probability normalized by n, it has a limit. So you have a large deviation principle, in other words.
Is it important that your two C's are the same then?
Yes, because, for example, if you take coloring, what does it mean that this is equal to this? That means that I can satisfy I can color all the edges. So this is not a coincidence. So I take n node graph with C times n edges. H equal to Cn means that I can color all of them.
So you have a very particular normalization of your H in mind, which before was.
Well, this H corresponds for coloring, or k-set, for example. So H means that it's 1 if it's different color and 0 otherwise.
Fully satisfied.
Fully satisfiable, exactly. Not nearly. It's fully satisfiable. Yep. Uh, Now, other questions or comments before I actually tell you about the interpolation method itself, because that's just, after all, what I wanted to. Yes?
It's positivity or negativity of this for satisfiability threshold, right?
Of which one? This?
Yeah, so now for satisfiability, this will say that you can satisfy all the...
I see. Well, not quite, because what might happen is that you might be non-satisfiable, but the likelihood of non-satisfiability goes to zero sub-exponentially. Let's say it goes like inverse polynomial. In that case, that probability would be log n over n would go to zero. So you would not be able to distinguish, for the same reasons as before, you're still not being able to distinguish it with the proper satisfiability. Somehow the hard satisfying all the constraints.
It's strict greater than zero, strict less than zero.
Yeah. Okay, so now let me talk about the interpolation and basically tell you how that works. You can safely forget about everything I said so far, because I could just start from ground zero, and just illustrate you using one example. And then the example is again independent set. So we have a Erdős-Rényi graph, n nodes, c times n edges. Let's I sub n be the size of the largest independent set in this graph. Okay, that's the object of interest. Our goal is to show that I sub n, the size normalized by n, has a limit. We want to show the existence of this limit. What we claim is, in fact, that when you think of n as a sequence indexed by, when you think of the size of the largest independent set as sequence indexed by n, it is nearly super additive. So that's what I want to demonstrate. The size of the largest independent set is at least the sum of the sizes of independent set of smaller graphs, n1 nodes and n2 nodes, with a little bit of correction which doesn't hurt you because we're looking at the linear scaling. So the little bit of correction here won't hurt you. So in other words, if you ignore this term, you have a sequence which is super additive. A super additive sequence normalized by n has a limit. That's Feketa's sort of simple exercise to show. It gives you the existence of a limit. It does not tell you what the limit is. That's the strength and the weakness of the approach. I should say that subadditivity or superadditivity is non-use in many random structures. First passage percolation, planar TS traveling salesman problem, many other problems. You can show the existence of certain structure by subadditivity without being able to actually say something concretely about that. Okay, so let me actually demonstrate that this is the case. Once we do that, we're done. And this is where the interpolation actually kicks in. What we're going to do is we're going to gradually interpolate between, on the one hand, Erdős-Rényi graph on n nodes, on the other hand, a disjoint union of two Erdős-Rényi graphs on n1 nodes and n2 nodes.
And n equals n1 plus n2.
And n equals to n1 plus n2, and c is deliberately kept the same. Same c here and c. So average degree is going to be the same. And on the left-hand side, you're going to have a big graph with n nodes. On the right-hand side, you're going to have a disjoint union of two smaller graphs, but the total number of nodes is going to be preserved. Huh? You will see. That's the part of the interpolation construction. You will see that I will actually, it's sort of like a coupling argument where I will gradually couple between this object and this object. But this limiting object is disjoint union. So I have one random graph and another random graph and no edges in between. That's what I want to interpolate in the end. Okay? So this is how we do that. We pick a parameter t between 0 and cn, and we generate t red edges and cn minus t, and the remaining edges are blue. Now let me tell you what are the blue edges and what are the red edges. Each blue edge is chosen uniformly at random from all nodes. So it just completely ignores this partition. That's what we do. Okay? Each blue node, each blue edge. Each red, so it looks like this. It might go across parts. It can be internal, like here, or it can go across. Doesn't matter. So the blue edges completely ignore the partitioning. Red edges, however, are generated by conditioning that they belong to one of the other parts. So specifically with probability n1 over n, we chose a red edge uniformly at random in the top part, and with probability n2 over n, we choose it in the bottom. So red edges always look like this. Okay? So they're always internal. Some blue edges, some red edges. Let's see what we have at the ends. If you have no red edges, all the edges are blue, you have c times n blue edges, you just recovered this graph. This is how you start. The other end of this, so you have something like this. If you have no blue edges, then all the edges are internal. So you have only like this, edges like this. And as a result, what you obtain is this joint union of two Erdős-Renyi graphs. If you follow carefully, and I hope you did not, but if you did follow carefully, you would realize that what I get here in the end is not quite c times n1 edges, because I have more like I have Cn trials with Bernoulli likelihood of n1 over n. So I get something close to that, but not quite. This is where square root of n correction comes in. But this is just a minor nuisance. It's really.
If you had used the Bernoulli model of the random graph, you wouldn't have this problem.
If I use the Bernoulli Poisson model, that would work.
Yeah.
Yes, and this is how actually physicists did it. But then you wouldn't have that, but you would have other headaches. You would have the headaches of having like a interpolation number of steps, which is random. So you need to resort to random stopping times and so on. So not a big deal. You can deal with that, but you don't have to. Okay. Okay. Yes.
Sorry, would you mind going to the last slide again? I didn't quite get it.
Yes. Last slide. Previous slide.
Yeah, the previous.
Okay.
I didn't quite understand
Okay.
what the purpose was.
So okay. So first case is when we have no red edges. So all the edges are blue.
Sorry, can you go so
Even more.
Yeah, sorry. So what exactly are you? What exactly are you doing here? Yeah.
Okay. So I'm generating for each t. I'm generating essentially a new random graph model, which has some edges chosen uniformly at random from all n nodes, and some other edges only from the top or only from the bottom. And what I'm saying is that this will sit right in between two extremes. One extreme is just Erdős-Renyi graph. The other extreme is disjoint union of two Erdős-Renyi graphs with smaller number of nodes. Yep.
Oh, okay. And then you argue that these two distributions are not so different from one another?
If
Which-
you argue like the independent set for t is at least as large as the independent set for t plus 1, then
Yes.
you're done.
Yes. Thank you. That's the next slide, but I want to make sure that, okay. So the claim is, in fact, to show something strong, indeed, as it was suggested, to show that at every step of the interpolation, you get actually an inequality. So a largest independent set on a graph with t red edges is going to be at least as large as the largest independent set constructed this way with t plus 1 red edges. So red edges hurt you, blue edges help you in some way. So that's what I want to show. And that's the interpolation idea, showing that all the way through the interpolation you have inequality. So let's show that, because even this is not, once you have this, then you have this inequality short of the square root of n corrections, but that's not a big deal. I'm sorry?
Is it true without the expectation?
This is true, not quite. There's some. You'll see. You'll see. That's actually part of this. So yeah, in some sense, you can take away part of the expectations, as you will see. So the way to show that. Okay, so let's try to see what really happens when you go from this graph to this graph. What happens is that, okay, you essentially delete one red edge and add one blue edge. Right? So that's the way. The difference between t red edges and t plus 1 red edge, essentially you delete one red edge, delete one blue edge and add one red edge. And you want to see somehow that in that way the size of the independent set can only go down. That's what we want to show. Okay. Yet another convenient way to think about it is to do the following: delete the blue edge, freeze the graph, condition on what the graph you obtain, call it G0, and then add a red edge, And yet another way to think about it is that take any graph, which you can obtain after deleting, add the red edge and add the blue edge, and compare the two possibilities. And that we will compare for arbitrary G0. So there is a part of it which is the deterministic analysis. So now I have to demonstrate the following fact. Any graph, G0, add the blue edge, namely uniformly at random globally, consider the largest independent set. Contrast that with any graph, generate a random edge either in the top or in the bottom with respective probability, consider the largest independent set, and show that in the second time you obtain in expectation something smaller. That's what we want to show. Now the nice thing is that all this expectation is about just the randomness of the one edge that you select. That's all you need to look at. Everything else is deterministic because we've conditioned on the graph G0 that we obtain. And this is now becomes almost an exercise, but I need a little bit of one extra technical step. Hopefully, I don't know if you're kind that likes to follow proofs or not. I particularly don't like following proofs during the talk, but some people do, and this is relatively simple. So let me give it a shot. Let I star be the intersection of all largest independent sets in G0. So it's something like this. The thing is that I have no guarantee that all the largest independent sets, there's only one. There could be many. One, another, third, fourth, and so on. So let me take intersection of those. There's only one? Fine. There's just one. If there's many, I'll take the intersection. Could be empty. You can show it's actually not empty, but that's besides the point. Doesn't matter. Okay, so you have this I star object. So, okay, so this is in the original graph. Suppose we add an edge. Could be blue, could be red. Puzzle. Suppose the edge is such that one end falls inside the intersection, one end falls outside of the intersection. The question is, what happens with the size of the largest independent set if this happens to be the case? So in other words, without this edge, I have largest independent sets. This is their intersection. I add an edge. What happens with the largest size? Doesn't change, right? And the reason is that, well, so what that I have one of the nodes inside all of them? I know that this node is outside at least one of them. Therefore, I can take this one and preserve the size. Adding edge can only hurt me. It cannot help me, but in this case, it doesn't. If I have two nodes which are outside, so much the better, even easier. Then in that case, still I have the same size of the independent set. However, if the edge is internal, then there is no way I can preserve the size of the independent set. Then I have to sacrifice, because all of them need both of these nodes. Now I have this edge. I have to sacrifice something, so it will go down. But it will go down by one, because all I need to do is to delete this node from any of the largest independent set. All of the remaining ones are now the largest. But the cardinality goes down by one, right? So that's a rather straightforward but important observation. So we can summarize it as follows. A graph plus an edge will have the same size independent set if at least one endpoint is outside, and goes down by one if it's internal. Now, the graph was arbitrary. It's only the edge which was random. So let's just simply compute the probability of the bad event, the event that both ends are internal. So the new size of the largest independent set will be the old one, minus the likelihood that two ends fall inside. What's the likelihood that two ends fall inside? It's the cardinality of this intersection divided by n squared. Both nodes need to fall inside. One falls inside with this probability. Another one, the n squared, is the likelihood that the edge is internal. Okay, this should be cardinality. Yeah? What's that?
Minus 1.
No, I allow repetition.
Oh, you allow.
Yeah, and if you look at the slide 1, which of course, when I defined my Erdős-Rényi graph,
You said n squared, not n choose 2.
I said, good. I said n squared. Wow, what a memory. Amazing. I said n squared, not n choose 2. But allowing repetition is actually not a big deal, because the number of repetitions is going to be constant. So you can clean it up. It's a matter of where do you want to take care of this nuisance, now or before. It's really, but I'd rather keep it clean like this in the interpolation stage and take care of this annoying.
We're not showing.
We're not showing. Yes, that's right. So if not, then indeed you would have some additional correction, but that's a good catch indeed. Okay, so you have this. In the case you add a blue edge, you have this correction term. In the case of red edge, however, let's compute the likelihood. Okay, so we have original term with probability. I shouldn't be. Okay. With probability n1 over n, the edge is inside the top part. The likelihood that both ends fall internally is going to be the relative size of the part of this intersection in the top part. So you have I1 star over n1 squared. Okay. With the remaining probability n2 over n, it's the same thing for the bottom. Okay. And now to connect the dots, all you have to do is to remember that x squared is a convex function and use the convexity property, because it turns out that this is smaller than the sum of these two terms by convexity. These are convexity weights, n1 over n, and 2 over n are sum up to 1. You have x1 squared, x2 squared is at least as large as when you put it internally. N's conveniently cancel, and I1 plus I2 is just the size of the full intersection. Okay? So by convexity, you have this inequality. And we are done. So we have shown that adding blue edge is less dangerous, or hurts you less than adding a red edge. Therefore, we have this conditional interpolation argument going back. I'm not going to go back. And then, therefore, you have a full interpolation argument in inequality in the right direction.
Oh, and now if you have sort of a more general model, then you have convexity in this larger space if you have sort of positive definiteness of this matrix.
And as it turns out that you have convexity for coloring, max cut, and some related models. On the other hand, annoyingly, you don't have convexity for something like mean bisection. Okay? So, unfortunately, it's a reasonable conjecture that if you take a mean bisection, just to remind you, the mean bisection means splitting nodes in two equal in cardinality size, such that the number of no edges in between is as small as possible. So it's the opposite of max cut. It's like a mean cut, but you condition the two parts to have the same size. Okay. Again, it's natural to conjecture that this limit exists. If you do the same kind of analysis, instead of a convex function x squared, you have an annoying function of the form x times y. X times y is not a convex function.
Like a disjoint union of two graphs,
yes.
And the mean bisection is, of course, can be, of course.
It's exactly. So because this mean bisection on this joint union is not the sum of two individual mean bisections. So you have another annoying fact of this kind. So that's all I wanted to say. Just a few notes. You can do the same analysis for the case of for the random regular graphs, but then you have to do more work. There's a whole bunch of annoying technicalities you need to deal with, but they're not particularly revealing anyway. So I chose not to do that. This generalization of what is the types of potentials that actually give you something is related to the issue of convergence of sparse graph limits. This is the whole development on its own. Recently, there's lots of interest in trying to develop a theory of graph convergence. In the case of dense graphs and sparse graphs, you can actually use this technique to say something about sparse graphs convergence, but that would be a subject of a different talk. And as I said, the method works in some models, but it doesn't work uniformly, even though you suspect that this conjecture should hold uniformly. There's no reason why this expectation should fluctuate. It should not. It should be limit always. But unfortunately, the techniques covers only some cases, not all of them. And the other big limitation of this approach is that it's non-constructive. Tells you the limit exists, doesn't tell you what it is. Doesn't give you ways to actually construct algorithms. Yes?
Just give you monotonicity that the limit is approached from below. So
yes, that's what I was referring when I think Martin asked, can you do something? What you can do in principle, take the largest your computer can handle, take maybe 30 node graph, brute force compute something, and that will give you some numeric bounds. That might be an interesting project for, I don't know, a summer intern or another graduate. Yeah. Huh?
Believe it or not, physicists do things like that. Sometimes.
I'm not,
then
yeah.
some mathematician proves that they're correct up to 4 digits, but they don't know the fifth.
Yeah. Well, yeah. No, that's. I mean, if it was of particular interest to get these numeric values, that would be. I think a more interesting question is actually developing algorithms which bypass some intrinsic difficulty. It has related to this clustering phenomena that I didn't talk about and so on. There is some fundamental obstacles to designing fast algorithm for these random structures. I think this would be a very interesting thing to do. You had a question?
You mean algorithms for estimating the limit, or algorithms for constructing solutions that approach the limit, or is that
either. For example, ideally the actual construct. So we have a largest independent set, normalized by n limit exists, but if I have a Erdős-Rényi graph, can I actually construct approximately, say, largest independent set in the random graph?
So somebody proved just some kind of divide and conquer scheme, but it's actually goes in the wrong direction, or is
I'm sorry, what's the?
The proof suggests some kind of divide and conquer scheme that you just graph apart. And
yeah, but no, it seems like the algorithm is sort of there, but what happens then, you need to analyze what's happening with the actual size of this I star. And that's not a very trivial object to do. So when you need to compare, for example, how this is different from this one. And for that, you need to know something about the size of I star. And we have no idea what the size of I star is. So the only thing we have this inequality. But actually handling, being able to say something constructively about this I star object.
Well, you can have an algorithm with this constant hardwired into, right? We know that I star is in the limit C star times n for some C star, right?
No, actually, well, I star is the intersection of independent sets. So it's actually, maybe with this approach you can show that the intersection of all independent sets normalized by n also has a limit. But again, even so you can do, yeah. But you still need to know where it is. If you do the actual algorithm, how do you know what belongs to the I star, what doesn't? Just knowing the size might not help, right?
Exponentially many of them, so there could actually.
There's exponentially many of them,
so
for
maybe
sure.
the intersection is a little smaller than.
No, because all the isolated nodes are there. All the isolated nodes, and you have linearly many of them, belong to I star, so it's not small. So it's non-trivial. But plus, you have isolated edges. No, that's isolated edge. It's I star is for sure linearly large, and it's not just all.
I say it's not linear large, but I say it maybe
The intersection.
smaller. The intersection, so the size of I star may be smaller than if you just rescale by the size, by the constant C you get for the largest independent set.
Yeah, I don't know about that. Yeah. I haven't thought about that.
So then you would have two different limits. You would have, you couldn't do what he says that I star is equal to the same C I'm trying to calculate times n, because it may be a smaller C.
No, yeah, I mean, it's a different.
Yeah, you just argued it was linear, but you didn't argue what the constant.
No, I don't.
Was the same.
I don't. Whether the constant is the same, it's for sure not the same. It's for sure not the same because you have linearly many isolated edges, and each endpoint of the edge is not part of I star because you can take either one or the other, right? So that means that on the other hand, each of them contributes to the largest independent set. So for sure, I star is smaller, linearly smaller than largest independent set. So that's I went like 1 minute over time, I think. That's it.
Yeah.
Yes?
So in the case of K-sub,
Yes?
what's the analog?
For the case of K-set, what's the analog of the statement?
No, so of the approach.
The approach would be, okay, so you think of the random K-set as an instance defined on a hypergraph. So each clause is like, if you talk about, let's say, 3 set. So each clause is 3 variables, and on which you put some kind of a negations with probability half. So you have a hypergraph, And what you do is you interpolate between the instance on n variables and c times n clauses on the one hand, and the other hand, n1 variables and c times n1 clauses, and n2 variables and c times n2 clauses. And you interpolate precisely the same way, exactly the same way. Yeah.
Like, what's the analog of the intersection of the independent sets? So you would like take the bits that are the same in all the optimal assignments, or is it
Analog? You mean what's the I star?
Yes.
I star is the yes. Oh, I see. That's right. So I star in the case of K-set is the variables which have to take the same assignment in every optimal. They're frozen variables. Yeah. And that's okay. That's an interesting thing, because if you take coloring now, you don't have frozen objects in coloring, because I can always relabel colors. There is no notion of frozen coloring in coloring problem. So in coloring, what you do instead, you introduce the equivalency relationship. You say two nodes are equivalent if they're forced to take the same color. That breaks it down to the class of equivalence classes, and then you apply this convexity idea on equivalence classes. So it's a little bit more work, but yes?
Would a similar technique be able to give you bounds on the variance of how far of how this of this quantity as a function of n?
Bound on the variance. Probably. I mean, you can get some. Sorry?
So you could try to gauge how quickly, if you were to do random simulations, how quickly you could expect to be near.
The bounds on the you can get the bounds on concentration using Azuma inequality, because and that's for that you don't need interpolation. You just know that largest independent set is concentrated around its mean by Azuma inequality, because the function which maps graphs to largest independent set is a Lipschitz in changing, deleting or adding edges. So just from that, you can construct the exponential concentration, not just variance. You can actually prove exponential concentration. Then indeed, so if you get some, you can get the bounds on actual expected value by computing it, by numerically computing the value, and then you can make statements about this, how close you are with high probability. So, but for that, you don't need interpolation method. It's just. Thank you.